Before we get into word problem applications, I want to take a moment and review some concepts from Chapter 4, which will be really important here. First off, I'm going to label this graph as y equals f prime of x. It's really important that you know what this is a graph of. It's not a graph of f of x. It's the graph of its derivative. And from the graph of the derivative, we can talk about a whole bunch of things about f by analyzing the derivative. So this graph goes from A to B, but some important points along the way are the zeros of the derivative function. So maybe I'll call that C1, and over here I'll call that C3, and over here I'm going to call that C5. The reason I'm labeling them with odd values is there are some peaks up here where we have horizontal tangents, and that horizontal tangent will occur at C2, and this horizontal tangent roughly there will occur at C4. Now the derivative is positive. This is a derivative graph, and the derivative is positive when it is above the x-axis, and the derivative is negative when it is below the x-axis, because this is the derivative graph. Now the function we cannot see is f of x, but we can say that f of x is increasing on the interval C1 to C3 in union with C5 to B. Do you remember the reasoning? Because f prime of x is greater than 0 on a corresponding interval. So the important part here is that f will be increasing where the derivative is positive. And we can also say that on the interval AB, the open interval, f has a local maximum. Do you see where the local maximum is going to occur? Do you remember why it's a local maximum? So the local maximum is going to occur here at x equals C3, and the reason for that is because f prime of x equals 0 at x equals C3, and f prime of x goes from positive to negative at x equals C3. So when the derivative goes from positive to negative, we have a local max. And of course we would have local minimums where the derivative goes from negative to positive. So at C1 and C5 as shown here. Finally, I want to talk about concavity, and I can say that f of x is concave. I'm going to choose one. I'm going to choose down or downward. F of x is concave downward on the interval C2 to C4. And then the reasoning of that is because, do you remember this? It's because f prime of x is decreasing on that interval, C2 to C4. Another way to think of that is to say f prime is decreasing, which means that f double prime is less than 0 on that interval. And so you can choose to say it either this way, reasoning, or this way. This one's what you're actually looking for, and I like to say the second one, but look for the first one. But you can choose which one you'd like to pick. Let's take a look at the first application. So let's read together. The graph of the function f, consisting of 3 line segments, is given above. So the graph that you see is the graph of f. But then the all-important equation says, let g of x equal the integral from 1 to x of f of dummy variable t. The minute you see this, you are already aware of the types of questions you're going to ask. And I really encourage you to come over here on the page and write, if g is the integral of f, then f prime of g is equal to f of x. So what does that mean? If this is a graph of the function f, then what is it a graph of? It's a graph of the derivative of the function g. The derivative of g of x. So all the analysis we use when analyzing a derivative graph is the same thing here, because this is a graph of the derivative of a function g that we cannot see. Part A, it wants us to evaluate g of 4 and also g of negative 2. So a long time ago, when you first learned function notation, you knew if I'm trying to evaluate the function at 4, I needed to plug the 4 in for the variable. In this case, the variable is x. So g of 4 is going to be the integral from 1 to 4 of, I no longer need a dummy variable, so I'll write f of x dx. In effort to evaluate this integral, I'm going to use the graph above and appeal to geometry. So I'm going to take a look at some of the geometric shapes that I will be considering. Whoa, drop that down and drop that down. So it looks like this brown region would be a trapezoid. Then we have the pink region, and then we have the blue region here. And we have to respect the sign being positive or negative because some of the portions are below the x-axis. This is a review of the prior unit. So I'm first going to find the area of the trapezoid. I'm going to use average the base. The first base would be the height of the brown, would be 4, plus the other height of the brown, which is 1. I'm averaging those bases times the respective height, which goes from 1 to 2, so that is a height of 1. Next, I'm going to look at the pink triangle, and that's going to be 1/2 times the base of the triangle, and the base of it is 1, and the height of it is 1. But now I look at the blue triangle, and because it is below the x-axis, I have to subtract the area when evaluating the integral, so it's going to be minus 1/2, base of 1, height, if you will, of 1. That's kind of nice because the positive 1/2 will cancel out with the negative 1/2, and all that I have to consider is the area of the brown. So that's going to be 4 plus 1 is 5 divided by 2, so the integral from 1 to 4 is 5/2. Now I have to evaluate g of negative 2. So that will be the integral from 1 to negative 2 f of x dx. But if I'm going to appeal to geometry, that assumes left to right, but you notice the negative 2 is in the top bound. So what I'm going to do is make this negative and flip it and go from negative 2 to 1 of f of x dx. So that means I'm taking a look at this triangle from negative 1 to 2, and I will take the opposite of the area of that triangle. So I have the negative out front, and then the integral from negative 2 to 1 would be 1/2 the base, and the base goes from negative 2 to positive 1, so it has a base of 3, and it has a height of 4, and that'll be 12 divided by 2. That's going to be a negative 6. Let's take a look at part B. In part B, it says find the instantaneous rate of change of g with respect to x at x equals 1. So in other words, the instantaneous rate of change of g is g prime, and we want to find g prime at 1. We want to find the derivative of g at 1. So what is the derivative of g at 1? Well, we come over here and say, I remember g prime is f, or f is the derivative of g. So in order to find g prime of 1, all that I have to do is evaluate the function f at 1. To evaluate the function f at 1, like we did when you first learned functions, I come over to the graph at 1 and I come up, and the output is 4. So f of 1 is equal to 4. Remember, this is the derivative graph. So if I want the derivative at 1, I need the function's value at 1. I would like to skip to part D before doing part C. In part D, it says the second derivative of g is not defined at 1 nor at 2. How many of these x values are coordinates of points of inflection of the graph of g? Justify your answer. The way I want to answer this is start off by saying g has a point of inflection at blank. I'll pretend I don't know the answer. G has a point of inflection at some x value. The reason for that is because g double prime of x, do you remember the reasoning? G double prime of x has to change sign. So we'll say changes sign at, I'll underline it because I'm pretending I don't know the answer. So the relationship here, though, is important. We want to say g double prime of x then will equal f prime of x. So because g double prime, which equals f prime of x, changes sign. So that's what I'm going to be looking for. I come over to my graph and I have to determine where the slope of the derivative changes sign. If I can remember that this graph is the derivative, then if I say the slope of the derivative, I am literally looking where the visual slope changes. So as I go up the curve here, the derivative is positive. You've got to be careful. The derivative of f is positive. Then as I come back down, over here, the derivative of f is negative, and the derivative of f is also negative here. So that means g double prime will be positive on the purple, and g double prime will be negative on the teal. So x equals 1. That's the only place where f prime changes sign. So g has a point of inflection at x equals 1 and only at x equals 1 because g double prime, which equals f prime, changes sign at x equals 1. Just take a moment to mark that off. I'll say g double prime of x is greater than 0. Then as I come over to the teal, g double prime of x is less than 0, and over here g double prime of x is less than 0. So g double prime changes sign at x equals 1. Now let's go back to part C. Before I do part C, I want to look at something here. The times when the graph is above the x-axis means that g prime is positive, and times when the graph is below the x-axis, g prime is negative. G prime positive, the function g is increasing. G prime negative, the function g is decreasing. Notice that here, g prime will go from positive to negative. And so before I even answer the question, I just want to write this statement. I want to say g has a local max at x equals 3 because g prime of x, which equals f of x, the derivative, goes from positive to negative at x equals 3. And we can't forget to say that g prime of 3 equals 0. That's the first derivative test. The question calls for what is the absolute maximum of g and what is the absolute minimum value of g. And I want to do this actually two ways. The first way that I'm going to approach it is using the closed interval test. So if you remember, to find the absolutes, you find the local and evaluate which is the absolute biggest and which is the absolute smallest. So I have a local extreme, and we just mentioned the local extreme above was g of 3. Now, to compute g of 3, I will take the integral from 1 to 3 of f of x dx, appeal to geometry like we did in the first example. This time I'll have 5 halves plus 1 half, which will be 6 halves, or 3. Next, I want to look at the endpoints, and that will be g of -2 and also g of 4. Luckily, we already found these values in part A. So g of -2 is a -6, and g of 4 was 5 halves. And I should be able to look at these values, 3, -6, and 5 halves, and determine which one is the biggest, which one is the smallest. And I will say 3 is the absolute max. And I will say that -6 is the absolute minimum. Notice they're saying the, not where, by the closed interval test. Now, when this question was first written, the intent was to find only the absolute maximum. And so I'd like to talk about another way to identify the absolute maximum. We know that g prime of x equals 0 at x equals 3. That's equivalent to what we said here. Then you could also observe g prime of x is greater than 0 on the interval -2 to 3, and then g prime of x is less than 0 on the interval from 3 to 4, which means something about the function g. It means that g is increasing on -2 to 3. It also means that g is decreasing on the interval 3 to 4. So if a function goes increasing, stops, and then goes decreasing throughout the interval, then there can only be an absolute max. It's when it changes from increasing to decreasing several times that the local extreme is not necessarily the absolute extreme. So the wording here or the written portion here in yellow could apply to finding just the absolute maximum.